second speaker today is Professor Okada, and title is on the slides. Please start.
Thank you very much. First of all, I would like to thank the organizers for the invitation to this seminar. And today I will talk about birational geometry of sextic double solids with certain singular points. This is joint work with Kurilov and it's difficult to say, Pemud. Okay. So first I talk about the situations in chaotic three-fours as an introduction. Okay, so I explain birational geometry of smooth chaotic three-fours. So let X be a hypersurface of degree 4, and okay, it is smooth chaotic threefold. And okay, this is of course Fano threefold and Picard number 1. So this is so-called modifiable space, of course. And okay, but take any smooth birational model Y and run minimal model program. Then we have output here, output of minimal model program. This output is modifiable space, and since this is threefold, it is one of the following according to the dimension of the base. So if base is a point, then it is Fano threefold and with Picard number 1. And next, if the base is a curve, then the fiber is a two-dimensional Fano variety, so it is a Deleuze vibration. And finally, the base is a surface, then it is a conic band. Okay, in general, we have this kind of output. But the important fact given by Iskovsky-Manning is that for any choice of this smooth birational model, Y, and for any minimal model program, for any choice of minimal model program, the output is always this type, Fano variety, Fano threefold, and moreover, it is isomorphic to this X itself. Okay, so we have the unique output, and furthermore, the induced map here. This is isom, I mean biregular isom. This is a result of Iskovsky-Manning. Okay, so I talk about the definitions of this property. So let X be a Fano variety of Picard number 1. So it is this X is viewed as a modifiable space. Anyway, it is birationally rigid if for any modifiable space V over S, such that its total space V is birational to X. For any such modifiable space, we have this isomorphism. So this X is a unique structure of modifiable space in the birational equivalence class of X. So this is a birational rigidity, and super rigidity is slightly stronger, much stronger. Okay, so it is birationally super rigid if it is birationally rigid, and this is okay group of birational self maps. This group coincides with automorphism. So, okay, sorry. Okay, so one remark. So this motivation, the study of this rigidity and super rigidity is motivated by the rationality problem of algebraic varieties, and simply because we have this implication. Super rigidity implies rigidity, of course, and it implies non-rationality of the Fano variety. Because rational variety has plenty of modifiable space in its birational equivalence class. Okay, with this definition, the previous results can be rephrased as follows. So a smooth Kartik threefold is birationally super rigid. So it is not rational. And the question is, how about singular Kartik threefolds? What happens for singular Kartik threefolds? Okay, so first consider the singularity, the simple singularity, this nodes, ordinary double points. So let X be a Kartik threefold with a node P. And let pi P be the projection from the point P. And it is generically finite of degree 2. This is 2 to 1, 2 to 1. So we have a birational involution interchanging these 2 points in the fiber. So we have birational involution here. And this is not biregular. So this is not biregular automorphism. So X is not birationally super rigid. And Mella proved that such X is birationally rigid. It's not super rigid, but it's rigid. So the assumption is as follows. So X is a Kartik threefold with at most nodes, no restriction on the number of nodes. But this property is very important. Q factorial Kartik threefold with nodes, then it is birationally rigid. Okay, this is one result. So the presence of nodes, how to say, breaks birational rigid, super rigidity, but it is still rigid. Okay, next. So before going to the next case, I introduce some terminal singularity of type CA, compound A singularity. So let P in X be so we say that the point P on a threefold X is a terminal singularity of type CAM or simply CAM point. If this point is an isolated hypersurface singularity, such that its general hyperplane section is dual singularity of type AM. Okay, and more specifically, so a point P is a CAM point if it is analytically equivalent to this hypersurface jump, the origin of this hypersurface. For some polynomial G with order m+1, so the so the least degree part is m+1, and in particular P is a CA1 point if and only if it is equivalent to this kind of hypersurface jump for some K. This is a CA point. Okay. In a similar manner, we can define CD or CE points, but in this talk, I only consider CA points. Okay, so let's consider singular quadratic threefolds with CA points. The firstly, it is not proved, but it is conjectured that any Q factorial quadratic threefold with only CA1 point is birationally rigid. This is not proved at all. And okay, so then consider CA2 point. Okay, let X be a quadratic threefold such that it has a unique singular point and it is of type CA2. So then Corti-Mellor shows that there exists another birational model. It is a weighted complete intersection of type 3-4 inside this space. Okay, anyway, this X prime is a Fano threefold with Picard number 1. And this X prime is birational to this quadratic threefold, and it is not isomorphic to X. So this immediately implies that X is not birationally rigid because it has another model. And Corti-Mellor shows that there's no more modifiable space. So they prove that X is birationally birigid. This is not defined, but this means that X is not birational to a modifiable space other than these two Fano threefolds. Okay, so for brief summary of birational geometry of quadratic threefolds, we have this table. So for smooth cases, the quadratic threefold is birationally super rigid, and if it has nose, then it is not super rigid, but still birationally rigid. And okay, if it has CA1 points, then it is also not birationally super rigid, but it is conjectured to be birationally rigid. And if it has worse singularity, CA2 point, it is not birationally rigid. So yes, we have this kind of situation. So okay, this is introduction of this talk. Okay, so yes, next I talk about the main results on six-stick double solids. So first of all, start with the definition. A six-stick double solid is Fano threefold with class number is isomorphic to Z and is generated by the anti-canonical device. So of course it is Picard number one. So in my talk, Fano threefold is always Q factorial. Okay, and has only terminal singularity. And okay, Fano threefold is class group isomorphic to Z, and which is a double cover of P3, branched along six-stick surface B. And in other words, X is isomorphic to a weighted hypersurface of degree 6 inside this space. Okay, Iskowski showed that smooth six-stick double solids are birationally super rigid. And then Chertsov and Pak generalized this result to nodal case. So six-stick double solids with at most nodes are birationally super rigid. Okay. And so next, so recently, so one of the collaborator of this talk, Pemel, investigated birational geometry of six-stick double solids with CAM points for various M. And in particular, he proved the following theorem. So firstly, under some generality assumption, six-stick double solid with CAM point, where M is greater than or equal to 4, is not birationally rigid. So he showed this by explicitly constructing birational map to some other modifiable space. And next, also under some generality assumption, six-stick double solid with CA3 point admits a birational automorphism, birational self-map, which is not biregular. So at least we can say that the X is not birationally super rigid. And after this consideration, he conjectured the following. So firstly, a six-stick double solid with only CA1 and CA2 points is birationally super rigid. Okay, super rigid. And if we admit CA3 points, then it is not super rigid, but he conjectured it is birationally rigid. So, okay, this is Pemel conjecture. And yes, here is the main theory of this talk. So our theorem is that sextic double solid with only CA1 points, CA1 point is birationally superrigid. And so, okay, this gives only partial, but partial answer to this conjecture. We cannot allow CA2 point here, CA1 point only. So some remarks. So in this theorem, no generality assumption is made. We do not need any generality assumption, and no restriction on the number of CA1 points. Yes. And second, this theorem gives, as far as I know, this theorem gives first examples of birationally superrigid Fano threefolds admitting a singularity other than cyclic quotient singularities and nodes. This is remarks. Okay. Okay, so this is today's main theorem, and okay, so next I explain some ideas of the proof of main theorem. Okay, so the main difficulty of the proof is how to say, lies, of course, lies in the CA1 points. So we need to treat CA1 points very carefully. And okay, so I explain this kind of things. First of all, I explain some generalities on the proof of birational superrigidity. So in this slide, let X be a Fano variety with Picard number 1. And okay, we will derive a contradiction by assuming X is not birationally superrigid. Okay, so suppose X is not superrigid, then by definition, there exists a birational map to some modifiable space, which is not biregular. Okay, assume this situation. Then firstly, take a very ample divisor H on V. Okay, here we have map and V, and take very ample divisor on V. So this complete linear system defines some embedding. And now set M to be the birational transform of this complete linear system. So, okay, this M defines this birational map. Okay. Then, okay, so because Picard number is 1, this linear system or any member of this linear system is Q linearly equivalent to minus nkx for some positive rational number. Okay. The following is this one is a fundamental result in the proof of birational rigidity. So it is called Noether-Fano inequality. Under the above setting, so X is Fano with Picard number 1, and assuming that it is not superrigid. Under the above setting, this pair X, and the boundary is movable linear system divided by this number n. So this pair is not canonical. So so we can rephrase this not canonical, where M is a general member. Okay. So in other words, there exists a prime exceptional divisor E over X satisfying this kind of inequality. Here, this number is nothing but the order of this divisor around this divisor E, and here, okay, here this exceptional divisor lives in some birational model, and this M is a general member of this out here linear system, and so this number is nothing but yes, this order, and this n is okay, yes, this n, and AEKX is the usual discrepancy along E. So okay, this inequality is called a Nater-Fano inequality. So roughly speaking, if X is not super rigid, then there exists a linear system which vanish along some locus to high order. And here comes the definition of maximal center. So, okay, this kind of E, divisor E, is called maximal singularity. And the maximal center is simply the center of this E on X. So in other words, subvariety gamma of X is called maximal center if it is a center of non-canonical singularity of this pair. For some movable linear system M, and yes, for some linear system M, and here the number n is defined by this relation. So if a Fano variety is not super rigid, then there exists a movable linear system M constructed in this way. And for this M, this pair is not canonical. So we have a non-canonical singularity, and so we have a maximal center. So to prove birational superrigidity, we need to exclude the existence of maximal center. So okay, I from now I explained some ideas of the proof of main theorem. So here is the main theorem. So let X be as in main theorem. So sextic double solid with at most CA1 points, and suppose it is not super rigid. Then, as explained just before, there exists a maximal center. And since X is threefold, we have the following three cases. So firstly, the smooth point is a maximal center. And next, singular point, in this case, CA1 point. is the maximal center. And finally, a curve is the maximal center. So we have three possibilities. And okay, for the completion of the proof, we need to exclude these three possibilities. So here is notation. So for a sextic double solid X, so I denote by pi the double cover, and B the branch divisor of double cover. So it is sextic surface. And yes. And yes, so I explain how to exclude these three cases. So, yes, firstly, talk about smooth points. So this is based on some local inequality. It is known as 4n squared inequality. So, okay, this is in a general setting. So let X be so let P in X be the germ of smooth threefold, and M is a movable linear system. So linear system without base divisors on X. And in this case, N is arbitrary. N can be arbitrary. N is a positive rational number. And if this smooth point P is a center of non-canonical singularities of this pair, then for general two divisors, D1, D2 of this linear system, we have this kind of inequality. So first of all, since M is movable, the intersection of general two divisors is defines a well-defined one cycle because M has no base divisor. So this one is an effective one cycle. So we can think about this multiplicity at the smooth point P. And since this pair is not canonical, these divisors vanish at P to some order. And this measures how much this kind of thing vanish at the point P. So anyway, we have this inequality. And the exclusion of smooth points on sextic double solids can be done by simply applying this theorem. So let me explain the proof. Okay, so go back to the sextic double solid case. Okay, X is a sextic double solid with some singularity. And I consider smooth points. So suppose some smooth point, P, is a maximal center. So in other words, there exists a movable linear system such that P is the center of non-canonical singularity of this pair. Here, N is defined by this rule. Okay, so next, to apply the previous 4n squared inequality, take general members of this system M, and then okay, here we have, oh, sorry. Here we have P and phi P here. And next, we take a general hyperplane of P3 here, such that this hyperplane contains this point pi P, but it does not contain any component of this effective one cycle. D1, D2 is one cycle on here, one cycle here, I don't know. D1, D2 is like this, and we push forward this one. So we have a one cycle on P3 passing through this point. And so we take a general H. So in order to set a general H, which does not contain any component of this image of this one cycle. Okay, then now we have this divisors. Di is of course Q-linearly equivalent to minus n kx, and okay, and this pi pullback of H is linearly equivalent to minus kx, and we know that this anti-canonical volume is 2. So we have this kind of inequality. So first of all, consider this intersection number, D1, D2, pi pullback H. So since D1, D2 is linearly equivalent to this one, and pi star H is this one, so we have this number. And because by our choice of H, we have this inequality. And here, this means local intersection multiplicity at P. Yes, and yes, it is bounded below by multiplicity of this one cycle. And finally, we have 4n squared. We have 4n squared inequality. So this gives a contradiction, and smooth point cannot be a maximal center. Okay, this. Okay, so the second part is the most difficult, or I mean essential part of the proof of main theorem. So exclusion of CA1 points, and we generalize 4n squared inequality for smooth points to a similar inequality for this singularity. So our theorem is that let P in X be the germ of CA1 point, and M is again a movable linear system of Cartier divisors on X. So okay, here this is a general statement. So this X is not a sextic double solid. This is just a germ of singularity. And let N be a positive rational number. So the setting and is the same. So if P is the center of non-canonical singularity of this pair, Then for general divisors D1, D2 of this system M, we have this inequality. So here the inequality gets weaker, 2n squared. And the one small remark, so in this case, P is not a smooth point. So it is, of course, singular point. So I explained the meaning of this multiplicity at the singular point. So CA1 singularity is isolated hypersurface singularity. So this one, so P is of course smooth point of A4. So this number is simply defined to be the multiplicity of the one cycle on this fourfold, smooth fourfold. But anyway, we have this kind of inequality. So once we have this kind of inequality, the proof of exclusion of points is completely parallel to the smooth case. So go back to this smooth case of smooth point. So the proof can be done by simply replacing smooth by CA1 point and this inequality by 2n squared. So let me explain the next slide. Okay. Yeah, this is the same as the smooth point case, but the difference is here. So let X be a sextic double solid with CA1 points, and suppose CA1 point is a maximal center. Then, as before, we have linear system M, and then we take divisors and the hyperplane section completely the same as before. And yes, and yeah, the computation is the same as the smooth case, but this last inequality gets weaker. But this is, of course, enough to derive a contradiction. So CA1 point cannot be a maximal center. Okay, so this is essentially the most important ingredient of the proof of main theorem. But the proof of this theorem is very complicated. So let me skip the explanation of the proof of this theorem, of this inequality. So finally, I explained the exclusion of curves. And this is not so difficult, but this case is complicated. So, but let me try to explain this case. So, okay, let X be again sextic double solid. And okay, firstly, we consider the following case division. So the maximal center, so in this case, we consider maximal, some curve is a maximal center. And so we have case division, 3 cases. We consider 3 cases. First one is the degree, anticanonical degree of gamma is greater than or equal to 2. And in the remaining cases, we have 2 cases. We have degree 1 cases. And first one is degree 1 and the image of this double cover pi gamma. This image is contained in the branch divisor, and the third case is not contained in the branch divisor. Okay, we need to prove in a different technique for these three cases, and we omit the second part. This is essentially follows from the Chertoff-Pax argument. So yes, by their argument we can prove the following. So let X be a sextic double solid without assuming some singularity. So arbitrary sextic double solid, and let gamma be a curve with anti-canonical degree 1. And if pi gamma is contained in the branch divisor, then it is not maximal center. So I don't explain the proof, but this case is known previously by Chertoff-Pax. So let's consider case A. So we have the following very useful lemma. So let X be a Fano threefold with Picard number 1. And let gamma be a curve. Okay, curve is always assumed irreducible and reduced. And if we have this inequality, then such gamma is not a maximal center. So we just apply this lemma. Okay, so yes, so again, let X be a sextic double solid with CF 1 point. And then as before, we have minus kx cubed is 2. So this lemma immediately implies that this curve gamma is not maximal center. So essentially, the most difficult case, curve case, is the case C. So I explain the remaining time. So for this case, we need to apply some other method. Let me explain the method. So let X be a Fano threefold with Picard number 1. And gamma is a curve on X. And assume that there exists a pencil of divisors on X with the following properties, 3 properties. So P is Q linearly equivalent to minus mkx for some rational number m. This is automatically satisfied, but the assumption is m is greater than or equal to 1. Okay, and the second general member of P is a normal surface. And so this assumption is this is assumed to consider intersection number on general member. Okay, but anyway, so for general members ST of this linear system, and we have the following. So the divisor T restricted to S is gamma plus delta. Gamma is this gamma, and delta is curve, irreducible and reduced curve, satisfying this kind of inequality. So this is intersection number on normal surface, yes. Okay. Yes. So delta is different from gamma. Under this assumption, we can conclude that gamma is not a maximal center. So I want to apply this lemma. Okay, from now on, the arguments get slightly complicated. So again, let's consider sextic double solid X, and let gamma be a curve satisfying this assumption of case C. So in this case, gamma is a smooth rational curve, and its image here, under double cover is a line. And by taking general hyperplane sections, general hyperplanes on P3 containing this line, of course, we have this one. Okay, we have this kind of picture here. And so set S to be the pullback of H1 and T pullback of H2, and define P to be the pencil generated by S and T. Okay. Then we have the following. This is clearly linearly equivalent to minus kx. And we can show that the general member, it's not difficult. General member is a normal surface. And finally, the restriction of these two divisors. So intersection of H1 and 2 is just this line. So intersection of pullback of these one has two components. In this case, two components here, gamma and delta. Okay, delta, yes, gamma and delta, where this is distinct, and delta is also the same time as gamma. So it is smooth rational curve, and the degree is equal to 1. And moreover, we have S here, and the singularity of S is contained in this intersection point of these two curves. Okay, this is slightly technical, but okay, by the okay, with this construction, these assumptions are satisfied, except for this inequality. So we have the minus kx delta is 1. In our case, we have this one is 1. So it remains to prove this inequality. Gamma delta, intersection number of gamma delta is at least 1. So this is a, yes, goal. So clearly, if these two curves intersect some smooth point of S, so we take intersection number on S. If this contains smooth point of S, then intersection number is clearly at least 1. So in the following, we may assume that they all intersection points are all singularity of S. And okay. So okay, we see that this intersection is 3 points counted with multiplicity. So firstly, we have 3 points. And the second case, it has this is multiplicity 2 intersection, and this is 1. And this is a multiplicity 3 intersection. So we are in one of these 3 situations. Okay, anyway, we want to compute this number, but for this, so let's consider first. Let's consider self-intersection number computed on the surface S. So we have this kind of formula, and we have this number is 0 because Ks is 0. Okay, and we need some correction term and attached to each singular point S, or namely this kind of intersection points here, and denotes correction term by CTQ. So in some case, correction term can be computed, and the correction term CTQ can be computed as this way. If this point is a dual singularity of type AM, M is this M, and for the minimal resolution of this AM singularity, we have this kind of picture. This is a minimal resolution of this point. So we have M minus 2 curves, a chain of minus 2 curves, and this number K is nothing but the position, intersection position of proper birational proper transform of this curve gamma. This here is gamma, sorry. And yes, if Q is of type AM, and if for the minimal resolution, gamma tilde intersects at only transversally at the EK. So in this case, we have this computation. Okay. So by this formula, we can show that for each intersection case, we have, in this case, for this point, the correction term is one half. And for this multiplicity point, we can show that CT is 1/2 or 1, maybe 1, yes. And for this multiplicity 3 point, we have 1/2 or 1 or 3/2. Okay, we can compute this way. So as a result, we have the summation of this correction term is at most this number. So in this case, we have this number. In this case, we have this number, and since this is multiplicity 1 point, this is 1/2. So in any case, we have this part. And by the previous formula, we have this inequality. And finally, we compute this intersection number in a straightforward manner. So we can write this way. And since this divisor, since this gamma plus delta is this divisor, so, and we have this inequality, so we have this inequality, yes. And since t is linearly equivalent to minus k, so we have this equality. And since this number is 1, we have this inequality. So we can show that this curve is not maximal center. And the proof of main theorem is completed in this way. So finally, I need, sorry, but I need one minute. So some remarks. So for a sextic double solid with at most CA1 and CA2 points, by the not same, but by the similar arguments, we can exclude the case 1 and 3. So we can show that the smooth point is not maximal center. We can exclude these two cases, curve and smooth point. And so if we can extend the 2n squared inequality to this point, then we can prove, prove the Pemberton's conjecture. Yes, sorry, thank you very much. I stop here.
Thank you very much. So is there any question or comment to this talk?
So is it possible to consider CD point?
Yes, it's possible, but yes, but it's possible, and it is important to consider CD or CE case. But the difficulty lies in the difficulty is to obtain this kind of inequality for such singularities.
Okay, thank you.
Any other question or comments?
Excuse me. So for the last conjecture,
Yes.
how about consider the singularity of CA3 point? Or higher.
Yeah. Thank you very much. Thank you very much. For CA3, we have okay. This is always true. Smooth point is of course okay for any singularity, allowing for any singularity. But this case, we have difficulty in the CA3 point. So curve passing through CA3 points, we have no control. So currently we have difficulty even for curves, and of course this one, we have no idea to obtain generalization of this inequality. So yes, this is some essentially difficult, I think, more than a CA2 case.
Oh, thanks.
Thank you.
So in CA3 case, do you still expect this is irrationally super rigid?
No. CA3 case, we have some birational. So CA3 case, we know that it is not super rigid. We already know, but so because blowing up these CA3 points, we can somehow construct birational involution, which is not an auto. So we know that it is not super rigid, but we do not know that birational rigidity.
Rigid, I see.
This is a conjecture.
I see. Thank you. So is there any other question or comments?
So in the CA3 case, do you expect that the evolution is the only birational map which is not regular.
Sorry, say it again.
So in the CA3 case, you say that it's possible to have evolution as non-trivial birational map. And do you expect that involutions are the only non-regular birational maps?
I expect so. But I have no confidence for some line passing through CA3 points. So I think this line, blowing up this line, does not create a birational map, but I have no confidence. There may be some involution, non-trivial involution, starting from this line, this kind of line. So because I cannot exclude this line case. So, but basically I expect this blowing up CA3 point, the birational map blowing up these points are all the involution I expect. Yeah.
I see. Thank you. Thank you very much.
Okay, so any other question or comments? Okay, if not, let's thank speakers. So thank you very much, Okada-san.
Thank you.
So the next seminar will be maybe in 2 weeks.